Yes, so next speaker is Dimitri Gangart from Birmingham.
Right. So, good morning, everyone. I would like to thank the organizers for letting me speaking here. It's such a nice conference. So, my talk is probably trying to convince you that there are some interesting things at equilibrium as well. And it is about calculating full counting statistics, weakly interacting Bose gas, and look for large deviation in this system. So it was done with my former PhD student, Maxim Arzamasov, who is now working in China, and there is also published recently. Right. So what is the full counting statistics? Very simple question, which is typical example of statistical physics module. What is the probability if you just take a gas of particles, no matter what are in what dimensions, you take a small volume and you ask what is the probability to find exactly n particles in the volume in the volume in some region. Then for calculation for non-interacting particles, it's particularly simple. Just do some binomial distribution, take the total number of particles to infinity, and here you have the Poisson distribution, with which characterized by by the number of particles, and this is the only parameter in this distribution. So, for example, if I want to calculate the variance, I calculate it and get that it is proportional to the mean number of particles. And the question would be, what are effects of various things? Of course, strong or non deviations, temperature, quantum statistics, and so forth. And these questions were addressed in different systems, and we decided that actually it should be addressed for the bosons as well. So here comes next slide. You might wonder what it does it mean. It's actually supposed to be a joke. So the joke is goes like that. Of course, what are the effects of correlations? And the joke is like that. Sherlock Holmes asked Dr. Watson what he thinks is the probability that next minute under their window on the Baker Street there will be 100 people going by. And of course, Dr. Watson say that the usual rate is 1 person per minute. So Dr. Watson, who knows the Poisson distribution on the previous slide, as well, that something can be estimated like I don't know, 10 to the minus 100. So it's really a very small number. And of course, Sherlock Holmes wins because the situation is rather like that, and we have a strongly correlated system here. So this is not a negligible probability. So that comes to the idea of bosonic bunching. This is well, it's not a good example of bosonic bunching, but one can always define something like that. If you have a total number of particles you want to observe to be n, but they like to congregate in some groups of the order of b, so then we have bm equals to n. M is the number of groups, and these groups are distributed like independent particles. Then the variance of the total number of particles will be eventually proportional to the mean number of particles times this coefficient b, which is the typical size of particles, people, soldiers in this group. And this number, this is just an example of something one can calculate, and this is the factor which depends strongly on temperature. And for example, and this is a very well-known example from either called log gas or free fermions, that for the generate fermions, this variance goes to 0, so B effectively goes to to 0, and we have an effect of anti-bunching rather than bunching. And bosons, of course, likes to congregate, and there is a bosonic enhancement. And one might think that indeed the quantum statistics will lead to the enhancement of this factor B. Well, now I don't think I am the person to convince you that 1D is an amazing world, and there are many reasons for that. Maybe the one of the most relevant to this group of people that actually things can be calculated. One can gain a lot of insight on the physical quantities, and moreover, this is not just an abstract question. It is experimentally accessible and realized system. All one has to do is just to squeeze the, say, if we're talking about cold atoms, we squeeze the atoms with some external magnetic field in such a way that the transfer confinement is the largest energy scale in the system, larger than temperature or chemical potential. This can be realized either by putting atoms into the crossing laser beams, creating these tubes of lattice of tubes, or using magnetic field of a chip, and then realizing this regime. Moreover, these atoms still interact, and the interactions are typically a short range. What is very good for us is that the interaction coupling, the interaction constant, can be adjusted, for example, by simply changing the transverse frequency. And this way, one essentially ends up with the famous Lieb-Lininger model, first continuous model solved by Bethe and Resuts, consisting of kinetic energy and interaction, short-range interaction, delta interaction, potential energy. This model, if we take some thermodynamic limit and some density of particles, depends on only one dimensionless interaction constant, gamma, and one distinguishes two regimes. One when gamma goes to 0 and we have weakly interacting, or Bogoliubov regime, and the interesting regime which was very popular is when gamma goes to infinity. In this case, the bosons in this system start to behave like fermions, and one can apply machinery of non-interacting fermions. In other words, one can also define the Latinger parameter, which is just a reformulation of this this interaction parameter by using the sound velocity, and in the weakly interacting case, the Latinger parameter is a very big number. For fermions, of course, Latinger parameter is 1. And I'm going to concentrate on the weakly interacting regime because I would like to convince you that actually this is the very interesting behavior happens as a function of temperature, where we have some sort of different scales which provide a change of behavior. Right. So what are these? So first of all, we have a quantum degeneracy temperature given by the standard expression. This is nothing but the Fermi energies. If the particles were fermions, that would be the Fermi energy. If the particles were three-dimensional bosons, that would be the temperature of the temperature of Bose-Einstein condensation. Now, 1D, this temperature essentially borders the classical behavior when quantum statistics doesn't play any role, to the situation when particles are non-interacting, but they start to feel that they are bosons. And in this case, one can convince himself that the density correlations decay with this typical correlation length, called phase coherence length, for reasons which are not clear right now, but maybe will become clear later, which is inversely proportional to temperature, and this is the correlation length in this regime below the quantum degeneracy. On the other hand, and here nothing depends on interactions. When temperatures are taken even lower, and I will tell you where, actually interactions start to play the dominating role, and the energy scale is given by the chemical potential, which is the coupling constants times the density, mean expressions to the lowest order, which can be also written as quantum degeneracy times the dimensions parameter gamma, which I remind you is a small number. So we have plenty of room between these two temperatures. In this case, decay of density correlations is dominated by the healing, so-called healing length, which is simply the characteristic length of the chemical potential. Right. So one can calculate this bunching factor I was mentioned before, namely the ratio of the variance to the mean number of particles, and one can see indeed that starting from higher temperature, somewhere this bunching increases and behaves like this, the inverse ratio of the temperature to the quantum degeneracy temperature, and in the absence interaction, it would actually diverge, which in some sense contradicts the idea that at zero temperature we still have a Poisson statistics. And right, so free bosons would be, the condensate has Poisson statistics of number of particles. However, one can see that in fact, starting from the low temperature, one can show that in some the bunching actually increases, so there must be maximum somewhere, and there is an interesting temperature where two typical scales, the healing length and the phase clearance length, are equal to each other. I would call this temperature the crossover temperature. It can be given by the square root of gamma times the quantum degeneracy temperature. Therefore, it's much larger than the chemical potential for weakly interacting Bose gas, but much smaller than the temperature of quantum degeneracy. So we have, once again, a lot of room to look at quantities like this. This is has some name in the standard classification of weakly interacting Bose gas. So from zero temperature to the chemical potential we have, and actually below this crossover temperature we have physics of quasi-condensate, which can be either cold, the Bouguereau bosons are rather quantum or classical. Above this temperature we have so-called decoherent quantum, the system of free degenerate bosons, and above the degeneracy temperature we have so-called decoherent classical regime. Yes? Oh, okay. So, well, in fact, this might be seen as a result of my calculation, but in fact, since it involves like the second order correlation function, it can be simply obtained from the known results for the second order correlation function. Okay, but I will come to this. Right. So, and this physics, the bunching phenomena, or the second order correlations, the variance, was observed in experiments in the group of Isabelle Bouchoul, where the idea is very simple. They use the quantum chip. They have confined the atoms to one dimension, so this is seen from the side, and take a picture, take absorption picture. This way they can get a lot of pictures like this, number of particles as a function of the longitudinal coordinate, and by making some statistical analysis of these pictures, dividing these pictures into pixels of some size delta, which is of the order of the characteristic lengths which I mentioned before, one can look at the variance of number of particles in such a pixel, and here are the first results, where this is the second moment, and this has to be compared. So this is actually the different temperature regimes. So one can see that at lower enough temperature, these black circles go well above the Poissonian linear dependence. The horizontal axis is the mean number of particles, and the vertical is the variance. So this is cannot be compared directly with the previous picture, for the reasons that actually this that crosses several regimes here, but I will come to the comparison later. Right. Now, these results, the theoretical predictions which are shown here, essentially are obtained from the simple thermodynamical argument, which goes like this. If one wants to calculate the statistics of the number of particles interval, so this kind of operator in the second quantization, the moment of this quantity, one is dealing with many point correlation functions. These functions are, of course, the curves of the beta ansatz or exact calculations. Very difficult. One have to find some way to calculate them, especially when the interval is sufficiently large. One has to know this correlation function at different points. But there is a shortcut. If the interval is very large, much larger than some characteristic length, correlation length either, which depends on temperature, different in different regimes, so it should be defined something like this. Then one can view the system of atom of this interval of R as some sort of subsystem immersed in a huge reservoir which provides temperature and chemical potential. For one can use the fluctuation dissipation theorem, namely relating the fluctuations of the number of particles to the response to the change of the chemical potential of the mean number of particles. Here is the density. So if one knows the equation of state, one knows everything, because now one can take derivative, calculate the second derivative, and obtain the results and plot the corresponding theoretical curves. And this can go on for any moment. One just changes the number of derivatives. And then, of course, this is maybe not the most economical way. So there was a recent, and this was experimental paper. However, well, on the other hand, one can also use some more sophisticated method, which actually amounts to be the same, but one can try to calculate the derivatives of the equation of states from the Young thermodynamics, so this type of equation one gets, and that was done up to the fourth moment in this paper. Right. So this indeed works very well when the interval size is sufficiently large. Large, again, I repeat, means larger than the typical correlation, the correlation length in the problem. On the other hand, there is a different regime, and this is where the beta ansatz can be used, namely when the interval is very, very small. Essentially, the interval is not an interval at all. The typical configurations of field do not change along the interval, and one can then get away with calculating the local correlation, the correlation of operators in the same point by using the beta ansatz. And this was done in a recent paper by people in this audience. And as what you see here is indeed not essentially all moments can be calculated like this as a function of for different values of k. So here it is. This is what is called full counting statistics, namely the number of particles in the interval of very, very small size, of the typical distance between the particles, which is the microscopic scale, and essentially this is the answer, which can be done in either in a ground state, after a quench, or in a thermal state. Well, however, I should just point out that this picture represents the typical exponential, I want to say exponential decay of the number of particles, which is not surprising. We have a very small interval, so there is some reasonable expectation to find there one particle. To find there two particles, three particles, decays exponentially with the number of particles. However, this is a nice and exact result obtained from the Betance and very sophisticated method. Right. So can we somehow mix the two? Can we, as I said, experimentally, the interval has a typical size of the correlation length, which is in a very wide range of temperature, is much larger than the typical distance between the particles. On the other hand, if we going to the scales, such short scales, the thermodynamics will not help. Can we do something in between? Can we use can we devise some simple method to address the problem of the full counting statistics? And the answer is you don't even have to solve Betance equations for this. All you need to do is to use semi-classics. And this is how we do this. So in this talk, calculate this quantity, but we rescale it properly. Namely, we look at the intervals which on one hand can be either longer or shorter than the correlation length, which and in the regimes we are talking about, the correlation length still contains a very large number of particles. Therefore, it is natural to define a rescaled distribution. We will define distribution of the ratio nu of the number of particles in the interval to the mean number of particles in this interval, and will, since the sort of the quanta of this quantity are very small, we treat this as a continuous variables, and this is well suited for the experimental situation. The pixels are of the order of the correlation length and much larger than distance between the particles. Now, and this is possible, as I said, in the regime when the correlation length is much larger than the distance between the particles. This is probably the main advantage and interest in the weakly interacting regime, because this is where it really holds. For the strongly interacting particles, for the free fermions, there's only one characteristic scale, which is the distance between the particles, nothing else. Right, so let us define two-dimensional parameters. Now we have the temperature measured in units of the crossover temperature. We can have this parameter either larger or smaller than 1. In other words, this is precisely the ratio of the healing length, the interaction dominated, the interaction related quantity to the phase coherence length. And as a different parameter will be the size of the interval with respect, well, one can choose any of these two length scales. Well, I have chosen the phase coherence length, therefore I have a different, this kind of diagram where the results will apply. So first of all, for sufficiently large intervals, namely when R is larger than phase coherence length, one can study our results will apply in a wide region between 1 divided by k. I remind you that k is the larger parameter and is the large number, and k. So in terms of the temperature, we are working between the chemical zero temperature chemical potential and the quantum degeneracy temperature. Now, what is meant by short or long intervals depends on the temperature. For high temperature, it is essentially either R smaller or larger than L phi. For small temperatures, it will be something more tricky, because in this case, the the coherence length looks like this, but still it provides a large space to go. Right, and some definitions we define. As usual, we define the generating function, which is the mean value of this exponent with some source term lambda, represented as a path integral. And in this path integral, we have the action which is obtained from Lieb-Linear Hamiltonian, depending on the temperature and chemical potential. But chemical potential is adjusted, so we have the given mean density and a source term, which can be written like this. We have just number of particles in the interval, this function. This funny combination stems from the fact that this is a not normally ordered operator, and if we want to replace the operators by the fields, we have to consider normally ordered quantities. However, as long as the typical number of particles is large enough, so we don't go to pathological situation when we have almost no particles in the interval, lambda is also rescaled with the typical number of particles, and in this case everything is dominated by small lambdas, and one can simply expand this factor to first order in lambda. And now comes the main trick which we are using in all this interval I mentioned for sufficiently high temperature, but not very high. Essentially our system is classical, namely the quantum fluctuations play no role. And one can essentially if I go back to the previous slide here, my action is defined on the strip between 0 and 1 over the temperature, and the fields essentially are tau independent. This strip is sufficiently short. In this case, the action we have can be relabeled and remapped onto by changing the position to the new imaginary time. What one see here is classical, the quantum mechanics of a particle moving in two-dimensional anharmonic oscillator, by saying that our fields are two real and imaginary parts of the coordinate of the oscillator, and x is now the imaginary time. And the particle moved, and this is known as a classical field method, used in this context for calculating correlation functions by Castan, Madone, and Jacopo Corusotto quite a long time ago. Actually, it's coming from the transfer matrix method, just a continuous version of transfer matrix method. The potential which one has actually it's a two-dimensional potential, but it depends only on the distance, and has harmonic part which proportional to chemical potential, and chemical potential may change sign. So for low temperatures we have some sort of Mexican hat, while for and then taken over by the quartic part, which is proportional. And this combination is proportional to interactions, and for high temperature chemical potential is known to be negative, and therefore we are dealing with this kind of one minimum potential. So once this picture is understood, the full counting statistics, or rather the generating function, can be calculated can be reformulated in some sort of quantum quench in this potential. So supposedly we adding the source field means modifying the quadratic part of the potential, right, for the time proportional to the interval length. So we have such a sort of protocol. We start with some configurations of the systems because we're talking about a system of infinite length. So at time minus infinity, it started with some ground state. Then we modify abruptly the potential. We add additional harmonic term. The wave function still is the same, but it evolves for time proportional to the interval length. Then we have a new function, and we just have to calculate the quantum mechanical overlaps between the old and the new function, which can be done either numerically and in many cases analytically. So this is the main idea, and this can be done, as I said. So okay, so for here I'm just quoting the results. Now, for if we have a long time interval, the thermodynamic calculations, which I mentioned before, translates into this language is the fact that we have the overlap calculated by the projection onto the new ground state of the new potential, and we have to calculate the overlap between the ground state of the old potential and the new one, and the calculation lead to the following results. At low temperature, actually results were known because what we have is indeed the ground state is essentially concentrated near the minimum of the Mexican hat, and this is nothing but quasi-condensate. Once we remove this potential a little bit, we have a system where effectively, yes? Yes. No, it's actually right. So the action itself, if I change the fields, is nothing but the sort of integral over time of something like the kinetic energy and the potential energy. So it's a quantum mechanical particle moving in this potential, and potential looks like this if I parameterize my field in this way. Now we have a source term. I should probably we have a source term to calculate the generating function. The source term acts during finite time interval, and the source term is proportional to essentially to the quadratic part. Right. So the calculation for low temperatures are quite easy because we had a ground state which is a Gaussian concentrated near the minimum of the Mexican hat. Then Mexican hat, this minimum is changed by the source term, and we have to overlap to Gaussian, which is Gaussian again, and so this is the answer. We have Gaussian form of this full counting statistic function with the variance inversely proportional to R. So, well, which is the standard thermodynamic result. We have variance smaller as long as the interval gets larger. It's just central limit theorem, and there is a certain dependence on the temperature. One can see how it goes for. So these are kind of very well picked function, which is nothing but the standard fluctuation of particles in a condensate. For high temperatures and long intervals, the situation is more interesting because this is not a this is actually an exact calculation. You might say it's non-interacting particle. I agree, but still it was nice to find an exact solution, and in between we can actually calculate the overlaps numerically, so one can look at the transformation between the very peaked distribution at low temperature to quite broad and also skewed distribution at high temperature for long intervals. And this is to your question, how do you calculate the bunching factor, because actually this picture encodes all the moments of the distribution. Right. So we can calculate, as I said, all the moments of the distribution and compare with the experimental results. So one, for example, can see we have a rescaled variables here because the experiment was performed for one certain set of interactions and temperatures. Here we have essentially the predictions in the right variables for all of them, but one can see this typical curve here is fully compatible with the experiment, with the theoretical predictions for the experimental data for the third moment, which was obtained via the beta ansatz. We did this using our method, and we also have the fourth cumulant as well. Right. For short interval, it's even more interesting, and both theoretically and sort of in terms of the results. So because for short intervals, what happens is that actually, if we believe that our fields do not change, by short I mean short with respect to the typical scale on which the field is supposed to change. And in this case, we simply can obtain our probability distribution, full counting statistics, as the absolute value of the ground state in this harmonic potential, this so-called Dirac-Kapitsa limit. We just applying the quench simply sort of adds the phase to the ground wave function, and everything can be calculated. And then one can gain the intuition what happens because for the short intervals in the low temperature regime, our potential is like that, and we have distribution again peaked at the mean number of particles, and which looks pretty much like a Gaussian. However, when we raise the temperature above the crossover temperature to the high temperature regime, the potential changes and it becomes essentially harmonic potential, and the ground state, of course, is strongly concentrated near small values of the particle. So essentially, what we have here is a situation when this is a fluctuation dominated regime versus the sort of classical condensate dominated regime at low temperature. In the ultimate high temperature limit, the distribution is simply exponential, and which can be interpreted in terms of the distribution of intensity of non-interacting Gaussian beams. And we can go on and calculate this for the whole transition for the intermediate intervals. For high temperature, we have an analytic expression, and that how our distribution transforms from the very peaked distribution at long intervals to the exponential distribution concentrated near small values of number of particles, so which shows the enhancement of the fluctuations of number of particles. For low temperature, the result remains Gaussian, but the width of the distribution changes as a function of the interval, and we have calculated this crossover function, which shows that this variance is essentially inversely proportional to the size of the interval, as it should be from the thermodynamic results, to a certain constant which only depends on the temperature. Right. And finally, we have results for the emptiness formation probability, which can be obtained by simply taking the source term to infinity. And in this case, at high temperature, we have the distribution the probability there are no particles in the interval whatsoever, which is a sort of parallel to the emptiness formation in the spectrum of random matrices of free fermions. Here we have the following answers. At high temperature, this for short intervals, this distribution is actually a power law. Remind you that this mean number of particles here is still supposed to be a very large number, which crosses over to the exponential decay, which is similar to that of the Poisson distribution. However, this factor here is a large number, therefore it is much easier to have voids of the size r than if you compare it to the standard Poisson result at high temperature. And at low temperature, we have Poisson result for short intervals, while for large intervals this factor is very large, and we have much reduced probability to find no particles in the interval r. So here is actually interaction dominated region, and here is the fluctuation dominated region, and this is in agreement with the previous results. So I probably done. So we have full counting statistics, which is a experimentally relevant quantity, because essentially this is the data collected at the experiments and can be directly compared to our predictions. The calculations are simple and do not require very sophisticated methods. Physically, what we find is that as a result of we find the interesting non-monotonic behavior of the bunching factor as a function of temperature. So bunching may be expected. Bosons would like to bunch, but interaction at lower temperature interactions dominate and want to sort of debunch them. This kind of fermionization, if you want, this is kind of parallel to the fermionization anti-bunching, when interactions act as fermionic statistics. This dependence of all the quantities is quite strong, and there remain some open questions where this method can be applied. Probably trapped system, which would require using some time-dependent potentials, trying to generalize it to higher dimensions, for example, by using some symmetric, so to say, some symmetric domains, or to the lattice systems. So I thank you for your attention.
Thank you. So questions?
Yes, the calculation and the thermodynamic limit and 1-point function